All right, welcome to today's class in Mathematics 1. Today we'll mainly be discussing Taylor series and Taylor polynomials, but before we do that, here's a quick warm-up question for you. Again, an exam question that you asked for. So I'll give you a few minutes to see if you can find a solution for that one. And as usual, I always also have a tweetback quiz about that running. So once you have a solution, submit your answer to tweetback. All right, quick show of hands. Who's done? Who wants some more time? Great. So let's take a quick look at the solution then. Give you 20 more seconds to submit your answer if you haven't done so. And here's your results. About 90% vote for 0, and of course that is the right answer. Just to do a very quick recap, of course you'll notice that pi over 2 is the root of the cosine, and that means this here is going to 0, and of course this is also going to 0, so we have a 0 over 0 fraction. Both numerator and denominator are of course differentiable, so this is a situation where you can apply L'Hopital's rule, hopefully, if the limit turns out to exist, but we can give it a try. And if we do that, well, what do we get? For the numerator, we need to apply chain rule, so we get 2 times the cosine of x, then we multiply by the derivative of that inner function here. The derivative of the cosine is the negative sign, so we get times sine x, and we also get a minus sign. Just put that in front here. And for the denominator, we just get 1. And well, of course, that means this numerator still goes to 0 because we still have the cosine in here. The sine is 1, so that's not troublesome. The denominator goes to 1, so we can just substitute x into that expression. We get 0 over 1, and that is 0. And again, please mention that the limit exists, so L'Hopital's rule may be applied. All right. Any questions about that one or about L'Hopital's rule in general before we move on to Taylor? Wonderful. It doesn't seem to be the case. All right. So then let's take a look at the next topics. All right. First, mainly a little recap. We pretty much discussed all that stuff already in a less general fashion, but we did have a few examples about that. So remember, if you want to have a tangent for a function graph at a point x star, then of course that tangent will pass through that point, like this line here does. So we'll touch the function graph at that point. And the slope of that tangent is given by the derivative f prime at that point. Okay, so how can we express that tangent? Basically, there's 2 useful ways of doing that. The first would be we can express it as a function. So if you say this line here is the graph of a function, how does a function look like? Well, basically, it's a function of that form here. So you have something times x plus a constant. Well, how do you get those? Well, of course, that something is exactly the slope, so that's f prime at x. And if you want to determine that b part here, what you do is you just substitute the point x star. You know the function value at x star, right? So of course the tangent also has to have that same value because it passes through that same point. So just substitute that into this equation, and then you solve for b, and what you get is this expression here. And here's a way to write that down in a form that's a little nicer, I think. It's this way here. So the tangent can be formulated as f at x star, the function value of that point that we pass through, plus f prime at x star times x minus x star. And I think if you do it that way, it should be easy to remember that formula. Right? Or of course, you can always do this solution process here, but it will be beneficial to remember that for reasons that you'll see in just a minute. Another possibility that we've also discussed in an example problem is representing that line here as an affine space. So we can also use a representation that says, well, this is basically this point plus multiples of a direction vector. right? You may remember that exam problem that we discussed, I think, last week. So we want a representation of that form. The graph here consists of those points. So we have x, and we have the function value of that tangent function, that here, at x. And if we just use that, well, it's easy to reformulate that a little. So we get this presentation here, right? So this is, unsurprisingly, the point that the tangent has to pass through, the point on the graph. And this looks very much the same as in the functional representation. Again, we have an x minus xr after some reformulation times f prime. Only difference is we add a 1 here, right? So this is still the slope, but of course you also have to move in x direction, basically. So what that means is the direction vector basically consists of moving 1 in x direction and then moving by f prime in y direction, right? And that will yield the direction of that line. Okay, I hope that doesn't come as a surprise. So basically what we have is this translation vector and this linear subspace. Usually it doesn't pass through 0, so it's translated so that it passes through the point we want. And of course, any other point on that same line would also do. Not any other point on the function graph, but any other point that is on the same line. If you rather want to use something else, that's totally fine. All right. And now Taylor basically is a way of generalizing that idea. So a tangent has two things in common with the actual function graph, namely one point. So it passes through that same point. It has a function value at that point is equal. And the derivative at that point is equal, right? The derivative of the tangent is its slope, and that is the derivative of the function at that point. And if you want to approximate functions better than with tangents, because you can ask, well, is there a way to have more things in common with the function? So in addition to the value and the first derivative, I'd also like to have the second and maybe the third derivative to be equal at that point. With the tangent, that doesn't really work because the second derivative is 0. So unless your function happens to have that second derivative, well, you're lost here. You can't change any more parameters. So you'd have to resort to some higher degree polynomials to allow that. And that's the idea of Taylor. What we want to do is we want to determine a polynomial of sufficiently high degree, let's say n, that has the same function value as f at a given point, and also the first, second, and so on until the nth derivative should coincide. And this tangent is just a special case. That's a polynomial of degree 1 that has the same function value at that point and the same first order derivative. Right? So if you want a second order derivative to also agree, we'd have to use a polynomial of degree 2. So we have enough parameters that we can determine. Right? So what we get is a local approximation of f around that point x star, same as with the tangent, but now even more parameters, even more higher order derivatives agree. So hopefully the approximation becomes better as we extend the degree. Of course, if we use higher order polynomials, it's harder to use that approximation in some insightful way, because it's hard to determine the properties of higher order polynomials, right? So for second order, that works pretty well. For third order, it's already becoming difficult. And if we have higher orders, well, it might not be of a lot of use to do that if we want to know something about the function behavior. It still might be a good idea computationally, because it's easy to evaluate polynomials. It might be harder to evaluate function values of the original function. So yeah, maybe this is still a good idea, and maybe it will still provide some insight. But for polynomials, anything that's higher than degree 2, 3, maybe 4, it's usually difficult to handle. All right, so how would such an approximation look like? Well, the idea is to start with the ones that we know already. Of course, we can start with an approximation of degree 0. That's just a constant. And then we just want the function value to agree. Well, in this case, we just use that constant as f of x star. And that's the Taylor polynomial of order 0. We already know how that works for order 1. That's the tangent, and we've seen that already. Right, so for that, the function value agrees, and also the first order derivative agrees. Now, if you want to extend that to order 2, we try to use the same notation here. So we write our polynomial in the form f at x star plus f prime at x star times x minus x star plus some constant we need to determine times x minus x star to the power of 2. Right? The nice fact about this is it's immediately clear that if you substitute x star in place of x here, all these will vanish and we just are left with that function value, as we should. Okay, so to determine that A2, well, we need these two things to agree. It's easy to see that the function value works. If we compute the derivative, it's also easy to see that we get exactly the right thing if we have the derivative here. And if you compute the second order derivative, what we get is 2 times A2. Right? That's just this 2 that's taken down here. And now we want that to be equal to f double prime at x star. So what we do have to do is we set A2 to this value, f double prime of x star over 2. Right, so it's a little more complicated than the first ones. We now have this over 2 thing in there. It's not that bad. And if we continue to degree 3, we just add a term like that. We go through the same process. And this time, if we compute the third order derivative, we get this power of 3. We get the power of 2. And then we finally get the constant. So what we have here is 6 times A3. And that means if you want that to be equal to f3 primes, we need to set A3 to this value. Or in general, what happens is, well, this degree is reduced by 1 in every differentiation step, and all those degrees kind of pile up and multiply. So what we get is some expression of the form n factorial. Okay, and that's where this general term comes from. So here's the general definition of the Taylor polynomial of order n of a function f at some point x star that is given by simply adding up those terms here. So we always have a term where we have the kth derivative of f at x star divided by k factorial, right? That comes from differentiating k times x minus x star to the power of k. And we sum up all of those, and that's called the nth degree Taylor polynomial of f at x star, and that is a function of x, right? So x star is a constant. We set that once, and we can write down the Taylor polynomial, and then this is a function of x. This is the notation we'll usually use. There's lots of notations for the Taylor polynomial out there. I'll stick to that one, but of course, if you are used to something else, feel free to also use that. Maybe add a short explanation if it's not obvious what you're doing. All right, so that's what's called the Taylor polynomial. The difference between the function value and the Taylor polynomial value at any given point x is referred to as the remainder, and we'll usually denote that by Rn if we need it. We'll not need it very often. Right, so basically that's the error that the approximation still has, and of course the error depends on the point x that we choose. For x equals x star, the approximation will be exact. And the hope is that at least close to that point x star, the approximation will still be good. But of course, if we move farther away from x star, it's probably going to get worse and worse. Right? And of course, one important question is, what can we say about that remainder? Can we bound the error somehow? So if you want an approximation that has a certain quality, a certain maximum error, which degree is necessary to do that? So that's one important question. And another important question would be, well, if we extend the degree to infinity and beyond, what happens? If we add more and more terms, first question, of course, is, does this expression even converge? So is that something that is useful? And if it converges, for which points, for which x values does it converge to the actual function value? It might still converge to something else. We don't know, right? So that's also a question we'll have to ask later on. All right, so this remark, that should be pretty obvious from the way that we introduced the Taylor polynomial. This Taylor polynomial of degree n is the unique polynomial of degree n that coincides with the function f at the value, the first order derivative, and so on until the nth order at x star. Maybe more, but it's only guaranteed for x equals x star, of course. Let's take a look at a couple examples before we go on here. So, graphical example. Let's say f is the function with this blue function graph here. This graph is the function graph of the function f. And we want to sketch Taylor polynomials into that graph. Let's start with the Taylor polynomial of degree 0 at the point -2, right? So this is our x value. We compute the Taylor polynomial there. And degree 0 means the function value agrees, and we have just a constant function. So if the function value at that point agrees, then of course the function value of the Taylor polynomial has to be this. So that green sketch here, that is our T0 at this point. Okay, please note that I'm using different points here to make this a little less cluttered. So this is not the same, those are not Taylor polynomials at the same point. That would look differently. T1, that is the tangent, right? An affine linear function. This time I'm using the point 2. So here's my x value 2. Here's the point on the function graph. And now I want that function to have the same value and the same derivative at that point. So in other words, I'm getting the tangent for that first degree Taylor polynomial. And here's an example for T2. This time I'm using 0 for the approximation. So that means at x equals 0. This is the point on the function graph. So that T2 has to go through the same point. It's a polynomial of degree 2, so a parabola. It has the same derivative and the same second order derivative as well. And that means it will look something like this, something like the function graph itself close to that point. So that means it's probably a function that looks something like that. Yeah, so this original f is not a parabola, something else. And that means this T2 will not coincide with f, but at least close to the point, it will be pretty close to the graph f. Okay, so that's the general idea in geometric terms of Taylor approximation. Now let's look at a simple example of how to compute that thing. So as a very simple example, we're going to consider the function e to the power of x, the exponential function. And if you want to compute the Taylor polynomial for that function, for let's just say we want to take the point 0, right? So x star is going to be 0 here. and we want arbitrary degree, then what we need to do is we need to compute the function value at 0. That's e to the 0, that's simply 1. We need to compute the derivative, and that's why this function is so nice. The derivative of e to the x is just e to the x, so nothing changes. And that means the kth derivative is also e to the x, so we know all that derivatives. And of course, then it's easy to compute the values of those derivatives at 0. Right? We just have e to the 0 all the time, so it's always 1. That means if we substitute that into the Taylor formula, right, remember that looks like this. And then we have a sum over the k's from 0 to n, like that. What we have to do is, when all those derivatives are 1, so we get 1 over k factorial, x minus and x star is 0, so it's x minus 0 to the power of k, or simplify just a little, x to the power of k over k factorial. Right? And basically you should be familiar with that. If you turn this into an infinite series, this is known as the Euler series. Yeah, so this will lead to the Euler series. We've seen that already. So basically that provides Taylor polynomials for the exponential function around the point 0. All right, 2 pretty simple examples. We'll discuss some more involved examples later on. Any questions so far? Yes. Sorry, once again? Yes. So yes, to repeat the question, all the formulas that we have discussed in the lecture can be used in the exam without any proofs. That's right, yes. All right, so next topics. Maybe let's first go to that topic here, Taylor series. At least part of that should be pretty straightforward. We know what a Taylor polynomial of a given degree is. And of course, I've already hinted at that. One question you can ask is, well, what if we extend the degree to infinity? What if we turn this into an infinite series? Will that work? Will that give us a useful approximation for the function? Or ideally, that should yield exactly the function that we started with. So generally, this term here, just taking that to infinity, that is called the Taylor series of f at x star, basically same notation, just not polynomial, but series. And then, of course, you can ask all that question. And the fact is, the Taylor series of a function might or might not converge for specific values of x. So often, you'll have something like the series converges in some interval around x star, but maybe not everywhere. Or it converges everywhere, or it converges just at x star and nowhere else. All of those might happen. So you can't just say this is a Taylor series, so it will converge. It might not. And it's even worse. Even if the Taylor series of a function converges, it might not even converge to what you expect it to do, and that what you expect it to do is converge to the function value. Right? We started with that. We wanted to approximate that function, and now we came up with an approximation that is infinitely good at one point, but at other points it might not work, even if we add infinitely many summands to our polynomial. So you'd have to prove that if you want to use it, and you cannot just expect that to work, unfortunately. Question? I'm not sure if I got the question right, but so what you are approximating, of course, is the function exactly at that point x star. That will work because it's designed to work that way. And very often you'll find something like the approximation works well around that point, in a certain range around that point. The range might be small or large, you don't know that, but usually that's the expectation. And that often works, but not always. There are examples where the approximation works at x star, but nowhere else. Might not even converge anywhere else, right? So that can happen. Of course, that's not the idea. We don't want that to happen, but you'd have to be on the lookout for that. All right? Good. So before we talk about remainders and errors, maybe let's take a look at a few examples for Taylor polynomials and Taylor series. And one example is the one that you had in the homework here. So here we have a function x ln x squared, and your task was to determine the Taylor polynomial T2f at the point 1. And maybe let's first ask what the Taylor polynomial is. I trust you all did your homework, so here's a quick feedback, a quick tweet back poll, sorry, to see what results you have. Give you one more minute to submit your vote here, and then we quickly discuss that. I'll have more examples of Taylor polynomials in case you didn't do that as your homework. All right, here's your answer. Most of you said the first option, x minus 1 squared, is the Taylor polynomial, and those that have this answer have the right answer. Let's quickly look at this. So the problem statement, let me just pull that up once again. The problem statement is asking for a Taylor polynomial of order 2. That means we need the function value, the first and the second order derivative. So let's start by computing derivatives and function values at the point 1. All right, this here is the original function. So we can compute the function value at 1 right away. If you do that, we get 1 times ln 1 squared. ln 1 is 0. Right, so that is 0. Then we need the first order derivative. To do that, again, we first use chain rule, so that is 2 times x ln x. Then we need to multiply by the derivative of that. And to compute that, we use product rule. So first differentiate the x, that's 1 times ln x, plus x times the derivative of ln x, that's 1 over x. And that should be the first order derivative. Quick simplification yields, this is 2x ln x times, well, here we get ln x plus 1. X over x is 1. So if we evaluate that at 0, we get 2 times 0, oh sorry, at 1, not at 0. We get 2 times 1 times ln 1 times ln 1 plus 1. And again, this here is 0. So that basically zeroes out all the rest. And then we need the second order derivative. All right, so let's try to compute that. Maybe let's rewrite that slightly. That's 2x ln x squared plus 2x ln x. Yeah. That's 2x ln x, right? Okay, so for the first term, we get, let's see, 2 times 2 times 2x ln x squared. No, let me start again. Sorry, I want to start with the x term. So this is a product here. This is a product, sorry, of this and that term. So I'll start with differentiating the first term, 2x, the derivative is 2 times ln x squared. Plus, then I have 2x times, and now I'm differentiating that second part here, and that derivative is 2 times ln x times 1 over x. Now that should hopefully be correct. Plus 2x ln x, almost the same thing. Again, a product of this and that. So again, I'm using product rule here. I'll start with differentiating 2x, that's 2. So that's 2 ln x. Plus, and then I have 2x times the derivative of the ln, that's 1 over x. All right, and I won't bother with any simplifications. Let's just see if I can substitute 1 in here. I get, let's see if that worked, I get 2 times ln 1 squared plus 2 times 1 times 2 times ln 1 times 1 over 1 plus 2 times ln 1 plus 2. And again, all those ln 1s evaluate to 0. So apart from this last factor, everything is 0, and that means I get 2. Okay, so remember the formula for the Taylor approximation. So T2 f of x at the point 1, that is k from 0 to 2, kth order derivative of f at the point 1 over k factorial times x minus 1 to the power of k. Or if I write that out, I get f0 at 1 plus f1 at 1 times x minus 1 plus f2 at 1 divided by 2. 2 factorial is just 2 times x minus 1 squared. And now remember, this was 0, this was 0, this was 2. So what we get is 2 over 2, that's 1, times x minus 1 squared. Okay, so basically the only problem here is that it might be some work to get the derivatives right, but other than that, it's just straightforward computation. All right, any questions about that? Now, if that's not the case, then I think I have 2 exam problems prepared here. That is the one. Maybe do this. Yeah, we'll do this right now. So this is from the exam 2019, I think, right? No, 2020 actually, 2021, sorry. Problem 9. And I have copied the actual exam statement here. I'll copy that to my notes later on. So the question here is similar to what we've seen before. Let f be an infinitely often continuously differential function whose graph is shown in the coordinate system below. Draw a sketch of the following Taylor polynomials into that graph. Clearly mark which part of your sketch corresponds to which Taylor polynomial, right? Of course, you should always do that. So our correctors don't have to guess which of the things that you put in the graph correspond to which of those 4 things here. So T1, f of x at 2, T1, f of x at 1/2, and T2 at 1/2, T2 at -1. So the question is, can you draw a sketch of those? I'll give you a couple minutes to think about that, and then we'll try to figure that out together. So let's see how you're doing. Who's done with the problem? Who would like some more time? Let's say I give you 2 more minutes to figure that out. All right, let's get started. Just to get a brief idea of who of you thinks they have the right solution. That's not very many. Who of you have no idea what to do? That's about the same number. That worries me. Okay, let's take a look at that. So as you can see, you got 8 points for this, basically 2 points for each of those. So that was intended as an easy way to collect points, and it worked pretty well. People did collect quite a few points there. Let's take a look at that one first. So T1 of f at the point 2. T1 is a polynomial of degree 2, so that's a tangent, right? An affine linear function. At the point 2 means we're at this x position, so this is exactly the point where the tangent has the same value as the function. And that means, let's use maybe green for that here. That means that Taylor polynomial agrees with the function in that point, and it has the same slope as the function, so approximately that should look like this. Right, so this is this T1 fx at 2. The second of those tangents, we'll use orange for that one. again t1, so that's again a tangent. Now at the point 1/2, so we are down here. Well, clearly at that point the function has a local minimum. So what is the tangent going to be? What is the derivative going to be? 0, exactly. Yeah, so the tangent looks like this. So what you get is that function here. That is t1 fx at 1/2. Okay, I do hope all of you got those two right at least. Well, let's have a look at the quadratic terms. I'll use blue for the next one. Same point, 1/2, but now I want t2. So this is a parabola that looks locally like the function. So at that point, you see the function looks a little like a parabola already. So basically, we'll have something that looks similar to that function here at that point. And that was the expectation. So hopefully, people sketched something that looked like that. Yeah, of course, that parabola would have the same apex as the local minimum here. So that's where they should coincide. Right, so that is this t2 f of x at 1/2. And then probably the hardest part of this was this last one, t2 f of x at -1. So -1, this is here. So we're at this point. If you wanted a tangent, that should be clear. It would be something like that. But now we want a parabola, right? And in this case, it doesn't make sense to put the apex here. Right? So some people drew something like that. That doesn't work. Yeah, because that would absolutely not have the same first and second order derivative at that function at that point, right? If you draw a parabola like that, then of course at the apex, the first order derivative will be 0. That is not the case for this function, and the first order derivatives need to be the same, right? So that doesn't work. Instead, what you need to do is a parabola that looks something like this. Right? That should approximately be the right solution. That is t of fx at -1. Okay, so don't be fixated on that apex here. Of course, the function can also agree with its Taylor polynomial at some other point. It doesn't have to be some prominent point of the approximation. Yes? The inverse of that, so what you mean is something like, I don't know, like that? I'm not quite sure actually whether people did that, but I guess I would have accepted that as well. As far as I know, that is the right solution. But it's like, I mean, pretty much using the available information and coming up with something that looks plausible was enough in that case. Yeah, so I guess I don't think anyone did that, but I guess I would have accepted that as a valid answer. Yeah. This parabola, can it be wider? I didn't compute it exactly, so I don't know, actually. I think it isn't, but that's just a guess, more or less. Yeah. Some people did draw it a little wider than that, like this, and that was also acceptable. As long as it was a parabola and the apex was the same, that was fine. Yeah, I just wanted people to get the general idea right. You did do the sketch? I can't quite recognize that. So is my solution right? Sorry? Maybe you can just come up afterwards. We can take a look at that. All right, so generally in problems like that, of course, what I want you to do is I want you to use the available information correctly, and I want you to show that you have the right idea of how that should look like. The details don't matter too much. Okay? Now, enough about geometry. Maybe let's take a look at some computational questions, because those are usually the harder ones. I'll copy that into the lecture notes before I publish them, so you'll have that as well. There's been one question on tweetback that I'd like to take as an opportunity of discussing, discussing one of the problems. Where's my mouse pointer gone? Still in here somewhere. How can I move that out? Here, it's back. Good. So I'd like to discuss 13.6 briefly. E13.6. So the question here, I think it was also an exam question at some time. I don't remember which exam that was. But it was meant to be one of the easy exam questions. Determine the Taylor polynomial T4px at the point 2 of the polynomial p given like that. I'll give you a minute to think about that. That should be sufficient. All right, time's up. Who would like to answer that question? Exactly, it's just going to be p, right? So T4p, T4p, let me write that down. X at the point 2 is exactly p of x. Why is that so? We have this polynomial p here, and what we're trying to do is we're trying to come up with a polynomial of degree 4, right, of the following form. We have some a0 plus some a1, x minus around the point 2, so x minus 2, plus a2, x minus 2 squared, plus a3, x minus 2 to the power of 3, plus a4, x minus 2 to the power of 4. All right, that's what we want, and we want to determine these a0, a1, a2, and so on, such that the function value is the same as that for p at the point 2. The derivative is the same, the second order derivative is the same, and so on until the fourth order derivative. Right? If we do that, basically what we do is we take the derivatives of both that t and the function p itself. Right? So if we take that, differentiate that k times, like that, and then substitute 2 into that derivative, that must be the same thing as differentiating p k times and substituting 2. We do that for k from 0 to 4. So what that will give us is basically 5 equations in these a1 to a5 that we can then solve for. Right? So this gives us a system of linear equations with 5 equations in a0 to a4. And that means we should expect to get a solution, and in this case, even a unique solution. Right? And maybe you remember that I've said before the Taylor polynomial of degree n is the unique polynomial of degree n that agrees with the given function in the function value, the first order derivatives, and so on until the nth order derivative at that point. Well, what is the unique polynomial that agrees with this polynomial p in all these points? Of course, p has that property, right? It agrees with itself in all these points. So if a Taylor polynomial is unique, it has to be p. And you can easily see it's unique if you just take all of these equations, and then you'll see that this provides you with an SLE that has a unique solution. So no other polynomial will do the same thing. Okay, and that's why if you approximate a polynomial with a Taylor polynomial of the same degree, you just get p back. Of course, if you use a higher degree for the Taylor polynomial, then all the subsequent derivatives will just be 0. So again, you just get p back. If you use a lower order, you'll get something different. But if you use the same order as the polynomial has, or some higher order, you'll just get back your own original p. And of course, that also means if you compute the Taylor series for a polynomial, there will always be a finite sum that's, again, the same polynomial, because at some point, the sum will just break off because all the other sums are going to be 0. Yeah? At the point where the derivatives turn into zeros, the sum just breaks off, and it's going to be a finite sum, and it's going to be exactly the polynomial you started with. Okay, so good question. And of course, if you realize this, this should be, I don't know, 20 seconds or so. So again, I think that was an exam question and was meant to get you easy points. And most of the people actually recognize that. And now you should too. All right, so let's finally get to something more challenging. Let's see, there's a couple of examples on that sheet, but I don't want to spoil the fun here. So maybe let's take a look at some other examples. Maybe I'll start with this one here. Keep the other one as a warm-up for next time. Yep. And I hope I don't have that on here anywhere. Right. So, first example problem of computational nature. Consider the function f defined on the interval from 0 to infinity with the values in the real numbers with f of x equals x times e to the x. And the task is to determine the Taylor series of that function. Around 0. So that's t f of x around 0. As usual, I give you a couple minutes to finish. Very quick show of hands, please. Who's done already? Who wants some more time? All right, let's take a few more minutes then. So for those who are done already, I'd be interested in a quick assessment of how hard you find that. So I've opened a tweetback quiz. Maybe you can submit your answers there briefly. Let me quickly check again. Who's done with that problem? Who needs some more time? Let's maybe take one more minute. So we still have time to discuss that. Good. So let's take a look at your results first. Most of you thought this was a rather hard problem. And I do hope that's because you're not used to that type of problems yet. Let's have a quick look at how we can solve that. So if you consider a function for the Taylor series, basically what you need is a general formula for the kth derivative of a function, right? So you need to get some idea of how that looks like. And the good first step is usually to just compute a few derivatives and see if you can discover any repeating pattern. Okay, so let's try and do that. First, of course, we always have f0, so that's the function itself, x times e to the power of x. That's easy. Then let's compute the first derivative. X times e to the power of x, we use product rule for doing that. Right, so let's first differentiate this part, x, that's just 1. So we get e times x plus x times, and then we differentiate e to the power of x. That just reproduces, so that is e to the power of x again. Right, so that's the first order derivative. For the second order derivative, let's differentiate that once again. Derivative of that is just e to the x. The derivative of that, well, we've just computed that, right? That was the original function. This is its derivative. So let's just copy that. And I guess at that point you can see what's happening. Maybe let's do one more. If you again differentiate that function, this just reproduces. This reproduces. And this is again the original term, which has this derivative, right? So what we get is e to the x plus e to the x, just copy those first two, plus e to the x plus x e to the x. So what happens? Well, this last term always reproduces, and it gives you one more e to the x when you differentiate once again. And all of these e to the x's just stay once you have first produced them. Right? So in general, what happens if you do the kth derivative is, well, you get k of these, right? 1 here, 2 here, 3 here, and then you get that term. Okay, so for the kth derivative, you get k times e to the x plus x e to the x, and that holds for k greater or equal to 1, or even 0 if you want to include that. Maybe let's do include that. Now we want the Taylor series at the point 0. Right, so we can just evaluate fk at 0, and basically that means this term goes away. So we're left with k times e to the 0. E to the 0 is 1, so that's just k. And now finally we can use the formula. Remember, that looked like this, and we need the kth order derivative at the point 0 divided by k factorial times x minus 0 to the power of k. K from 0 to infinity. So if we substitute our results, well, what do we get? K from 0 to infinity. This kth order derivative at 0, right? This part here, remember what we got here is this. So we get k divided by k factorial times x to the power of k. Well, that means the first summand for k equals 0 has a 0 here, so that just vanishes. And for all the others, we can simplify that. So let's start with k equals 1 then. where k divided by k factorial is 1 over k minus 1 factorial. Times x to the power of k. And that's our Taylor series. And now you may be wondering, just a second, why that looks familiar. And let me show you a neat little trick to come up with the same result. So here's an alternative approach. Remember the function f is x e to the power of x, and we already know the Taylor series of the function e to the power of x around 0. Right? Remember? That looked like this, x to the power of k over k factorial, k from 0 to infinity. So one way to determine x times this thing is to just multiply x by that series here. We know it converges, so we can do that. And that will give us exactly the same result. Right? Just need to simplify that a little. All right, question. So this step here? Maybe let me just add one more step in between that. So let's split off the summand for k equals 0. That is equal to 0 over 0 factorial x to the power of 0. And then the rest from k equals 1. Like that. Is that clear? I just consider the first summand for k equals 0. I consider that separately. So here, this is k equals 0, this is k equals 0, and this is k equals 0. It's just to make it nicer, yes. Yeah? And then what I do is I say, well, this thing here, that clearly is equal to 0, so forget about that. Yes. So if that had been an exam question, that answer would have been sufficient as well. That step is just to make it nicer. All right. Any more questions about that? Then we'll continue our discussion of Taylor polynomials and Taylor series tomorrow. We will also take a look at the error of approximation, and that might prove to be the real challenge here. So look forward for tomorrow for more exciting problems of that kind.